Have you ever just looked at an AI and wondered, how? How does it actually know the difference between a dog and a cat? How does it rate a poem or create an image out of thin air? Honestly, it can feel a little bit like magic. But today, we're going to pull back that curtain and take a look inside.
This right here is the big question, isn't it? And the answer isn't about ones and zeros in the way we usually think. To really get our heads around this, we need a much better metaphor than just computer code. So instead of a computer chip, I want you to picture a gigantic stadium just filled with 10,000 people. This team, this crowd, has only one job: to look at an image and collectively decide what it is. And here's the key: this team of voters is our neural network. Now, what's so wild about this is that no single voter sees the whole picture, not even close. Each one is a hyper-specialist. One voter's entire job is just to identify the exact curve of a cat's ear. Another one only looks for the glint in an eye. That's it. They're experts in one tiny specific thing.
But this team isn't some chaotic mob. No, they're actually organized into three main sections, or rows. The first row, that's the input layer. They're like the network's eyes. They take in all the raw pixels. The middle rows, the hidden layers, that's where all the real thinking happens, where they analyze all those tiny features. And then you have the final row, the output layer, and they're the ones who make the final call.
So how do they all talk to each other? Well, the voters in that first row see their tiny little patch of the image, and they pass a note to the voters in the row right behind them. The note might say something like, "Hey, I'm about 80% sure this is a patch of fur," or "I'm 95% certain this is a pointy ear." And this chain reaction just keeps going, layer by layer, with each row building on what the one before it found. Okay, but that brings up a really important question. Is the note from our pointy ear expert just as important as the note from a voter who just saw, a blurry patch of background? Should they really have the same amount of influence on the final decision?
And this is where we get to the secret sauce of a neural network. The answer is a hard no. All votes are absolutely not equal. Over time, the network learns to give a louder voice to the voters that are more reliable. That vote from the ear expert? Yeah, that's treated as super important. The vote from the blur detector? It's pretty much ignored.
Now, in the technical world, this whole system of influence has a name. It's called weights and biases. It's basically the control mechanism that manages the flow of information. It strengthens the connections that actually matter and weakens the ones that don't. It's how the network learns what to pay attention to. All right, so our team is all set up. The rules are in place. We show them their very first image. It's a picture of a cat. The notes start passing. The votes are being tallied from one row to the next, and a final decision starts to build. And the final voter stands up and declares with absolute confidence, "It's a dog!" And this is what happens at first. The network has no idea what it's doing. All its weights are totally random. It's really just guessing. Completely and utterly wrong. But, and this is key, this exact moment of failure is the single most important part of the entire process. Because this right here, this is where the learning begins. So how does a digital system of voters actually learn? It can't feel disappointment. It doesn't get a pep talk from a coach. How does it get any better? Well, what happens is a signal gets sent backward through the network, kind of like a coach reviewing the game tape. That coach tells the whole team, look, the right answer was tat, not dog. So every voter who shouted dog, we're turning your volume down. Every voter who whispered cat, we're turning your volume up for the next round. This whole process of learning from your mistakes is called backpropagation. And the crucial thing to understand is this is not a one-time fix, not at all. The network is shown another image, it makes another guess, it probably gets it wrong again, and the weights are adjusted again. This whole cycle of guessing, checking, and adjusting happens millions, sometimes even billions of times. So what are these votes and adjustments, really? Underneath our whole voter metaphor, it's all just math. We're talking millions upon millions of tiny, incredibly simple multiplication and addition problems. Each vote is just a number. Each adjustment is just a tiny change to that number. Now, by itself, each one of those little calculations is completely meaningless. It's nothing. But when you chain millions of them together and you refine them over millions of tries, something really incredible starts to happen. All of that simple, boring math, it becomes intelligence.
There's a beautiful scientific word for this: emergence. It's the exact same principle that allows millions of individual ants, each one following super simple rules, to somehow create a complex functioning colony. It's how millions of simple calculations create the complexity of what we call artificial intelligence.
When you really step back and think about it, what we're watching is a kind of hyperspeed evolution. Instead of the billions of years of trial and error we see in nature, we are literally witnessing a digital brain go through millions of generations of learning in just a matter of days or weeks. And that kind of leaves us with one last big thought. We've just talked about how the system learns to recognize things, how it learns to see. But what happens when these exact same principles are applied on an even bigger, more massive scale? What happens when millions of these digital minds learn not just to see our world, but to start creating new things within it?